Okay, now we're into the fun part of the problem. Again, while we're doing this all together, individually, each of these problems we've already done in our day 1, day 2, day 3, so on and so forth. So right here, we're basically saying we're going to add 15 milliliters of NaOH. And in fact, when we look at a titration, we want to look at every single piece of the titration as its own unique problem. Because if we try to calculate it as it goes along, the volume is changing at some rate. And so we have a rate of change problem. We have to use some form of calculus to be able to do that. And our class is not calculus based. So we're going to look at it only at time 0 and at time wherever we are. And right now we're at whatever time it took to add 15 milliliters of the NaOH. Well, at this point, the reaction that's going on is a little bit different. We've got OH ions are combining with our acid, our HNO2. And again, that OH is such a strong base that it's going to react with any of these that are around. And I can tell just by looking at this, since they're the exact same molarity, I know that 15 milliliters of NaOH is going to run out before the 100 milliliters of the acid does. So, as I think about this problem, what I realize is going to happen is that this OH is going to pluck this H away to make a water, and then we're going to be left with an NO2 minus ion. Now, if we're paying close attention, hopefully we realize that, I'm going to switch to a highlighter, see how this works. We realize we've got, not that happy with that highlighting. So I'm just going to go to underlining instead. I have got an acid and his conjugate base. So if I can find out what the equilibriums are, or what the equilibrium values of these two things are, I can use the Henderson-Hasselbalch equation to be able to figure out the pH. And that's going to save me so much time. But I'm going to draw a line here so we have some room to work. But when I'm combining these, again, volume's changing, so I can't do my table in molarity because molarity is constantly changing as the NaOH is added in. So I'm going to do my problem in moles. So to do my problem in moles, I first have got to figure out initially how many moles of each of these do I have. It's the exact same calculation, just with different volumes. We'll start over here with the acid, since it says NaOH over here. We're going to do the acid over here in this part. And I know that I've got 0.1000 liters, 100 milliliters, that's an L, times my molarity, 0.50 moles, and that's a moles per liter. So in other words, for my acid, I have 0.100 liters times 0.5 moles per liter, or 0.05 moles. Now, 0.05 moles would be, without the appropriate number of significant figures, looking at this would be 0.050 moles of this guy. Well, the exact same calculation happens over here for NaOH, except for I don't start with 0.100 liters. For NaOH, I'm starting with 15 milliliters, or 0.015 liters, times a molarity. It's the same molarity. Again, I'm not using the same number. One number's here and one number's here, but they happen to be the same molarity. And when we do that, we get an answer of 0.0075 moles of NaOH. So 0.0075. Again, that's a decimal out there. Well, we have less moles of the OH, so as we go through our equilibrium expression, and again, we don't have any of this guy yet. Again, we're doing before we actually add them together. Well, we're going to lose every ounce of this 0.0075 moles of OH. Well, since it's a 1-to-1 ratio, that means we have to, if 0.0075 of him is going to react, 0.0075 of this guy have to react, which means we have to gain 0.0075 of the NO2 ion. Again, these are all in moles. So I'm going to end up at the end with 0 OHs. They're all gone. They all reacted. I'm going to end up with 0.05 minus 0.0075, and that value is 0.0425. And you might argue with me that that's not the appropriate number of significant figures, and I don't have an argument to go against that, but I've already done the math with that number, so I'm going to continue along. Of course, you could do it with 0.043 if you wanted to. And this would be 0.0075. And as I said, at this point, we've got nothing else in the way. Water doesn't matter because there's so much of him. And the OHs are all gone. So now I have a Henderson-Hasselbalch equation where I can easily find the pH by saying it's equal to the pKa, or in other words, the negative log of the Ka value, 4.5 times 10 to the minus fourth. It's a bad 10 to the minus fourth, but oh well. Plus the log of, since I did Ka, my acid's going to go on the bottom. This guy's my acid, 0.0425 over 0.0075. Now, if you didn't notice this as a Henderson-Hasselbalch equation, that's fine. You'd have to ask yourself, though, then, well, what's going to happen with these two? They're going to react with each other. They're going to make HNO2. You do an equilibrium problem, set it equal to Kb. We really want to get to the point where we can recognize right away we've got an acid in its conjugate base, and we're going to use this Henderson-Hasselbalch equation. And for this problem, the pH should turn out to be 2.60. Going back to my graph on the back page, now I can graph a point. I'm at 15 milliliters, so this is my X value, 15 milliliters, and my pH is 2.60. The pH did jump up a little bit because before it was pure acidic. Well, now we're starting to get some of this conjugate base in there. We've created a buffer solution. It's still not a very good buffer solution because it's so heavy on the acid. There is, ballpark 7 times, 7 times 7 would be 49. So there's ballpark 7 times as much acid as conjugate base. So it's still a pretty acidic buffer. That being said, as we go through these, you're going to see real quickly, there's a pattern. There's a real easy pattern, and I'm going to do each problem both ways from here on out. I'm going to do it the real easy way for those of you who are ready to see where these numbers are coming from, and I'll do every problem going through this ICE table in case you need that extra support. But look where these numbers came from. This right here, 0.0075, the number of moles of the conjugate base is exactly equal to, let me undo that, since that line's in the way, that value is exactly equal to the number of moles of OH we started with. And then, of course, if we use that many moles of OH, we're going to lose that many moles of HNO2. So it really would be just as easy to look at this problem and go back with the idea that we know, again, it's the same problem. We haven't moved on. It's still problem C. With the idea that we are adding 0.0075 moles of NaOH, and that means we're going to make 0.0075 moles of NO2 ion. So we can start off just with this values. We've already got our NO2. Well, we know if we use that much OH, we're going to lose, we had 0.050 moles of our HNO3, and we're going to have that every single time. We're always going to start with that value. Well, and we're going to lose 0.0075 moles of it when it reacts with the NaOH. And so we know we end up with 0.0425. Well, I've got those two values, that value and this value, and I can just go ahead and plug them into the Henderson-Hasselbalch equation. If I can understand and picture what's happening in this acid-base reaction, I don't have to go through the hassle of that whole ICE table. Again, if that's something that's not clear to you and you have no idea what I'm talking about right now, or as you look at the next ones, it's not making sense, there's nothing wrong with doing the ICE table. There's nothing wrong with going through this. It just takes a little bit of extra time. If you actually understand what's taking place here, it's really just a stoichiometry relationship between them. This is our limiting reactant, so he's going to make as much of the NO2 as possible. He's our reactant in excess. Well, how much is left over? 0.0425 moles. And so I've got my two values that I need for my Henderson-Hasselbalch equation. I know Ka, that's something that I can calculate once, and it's going to be the same the whole entire problem.